So let's get started with the Drude model. So we're going to talk about electrons in a metal, and we're going to use a classical approach to study electrons in a metal, and that's called the Drude model of metals. This is the first model for metals, and obviously it is based on a simple classical approach because that's the logical way to get started. And our fundamental aim in studying metals is to understand their basic properties. Now, what is the basic property of a metal? We know from childhood that metals are very good conductors of heat and electricity. Why is that? And metals reflect light. Not all metals, because metals oxidize fast. If you clean the get rid of the oxidation and expose the surface, then you will have a very bright reflection. Why do they do that? Metals are ductile, metals are malleable. You can draw them into wires, you can flatten them, you can hammer them without them getting broken, and so on. So these are going to be the basic properties that we need to understand from a very fundamental point of view. Why do these happen? So Paul Drude used the kinetic theory of gases as a base. Now, the kinetic theory of gases is what you must have studied in school. It simply uses the idea of collisions. We assume that the molecules in a box collide with each other and probably with the walls of the box. We don't assume there are any interactions between the molecules. The molecule is free, but it just, there is a relaxation time and there is a mean free path. So mean free path represents the typical length, average length from one collision to the other, and the mean free the relaxation time is the average time between collisions, and so on. So the starting point is to define which electrons in a metal are free. So we'll take an example of sodium. Sodium has an electronic configuration of 1s2, 2s2, 2p6 and 3s1. That's 11 electrons, so it must also have 11 protons for the atom to be neutral. And we now know that the first 10 electrons, that is 1s2, 2s2 and 2p6, are usually called the core electrons, and they are not free to move. So if I take the charge of the nucleus and add it with the charge of the first 10 electrons, I will get an effective charge of +1. The 3s1 is usually called the valence electron, and that is assumed to freely move around the metal, around the solid. And so that 3s1, obviously that one electron has a charge of -1. So this +1 and -1 is thought to be a modified atom. So that +1 will be the effective nucleus. But the question is, how do you know that 3s1 alone is the valence electron? How do you know that? How do you know why can't 2p6 or why can't 3 electrons from the 2p shell be part of the valence electron? That's a very deep question that requires a better understanding of the Pauli exclusion principle. You will be doing that partially in this course, but the majority of the Pauli exclusion principle will be dealt with in the statistical physics course, which, if I am not wrong, is being held in parallel with this course. So we will try to answer this question later on in the course, but for now we will not worry about why, how and why we define what is a core and what is a valence electron. Just that we will assume that for a given metal, a few of its electrons will be free to move around the solid, and a few will not be free. They'll be bound to the nucleus. So this is the fundamental assumption of Drude. So he assumed that the nucleus can be modified to this kind of a picture in a solid, where you have the nucleus and then there is a core shell. That's the core electrons. That's the modified nucleus, and then the valence electrons are become the conduction electrons in a metal, and these conduction electrons are free to move all over the metal. So now I can define the number of conduction electrons per unit volume. So small n is the number of conduction electrons per unit volume, and this number capital N is simply Avogadro number of atoms per mole, and each atom contributes Z electrons. So Avogadro number into Z is the capital N, and this volume is basically I can write it in terms of the atomic mass divided by the metallic density, and I can compute it. I can also define a volume that is available to each conduction electron. Now I can invert this small n and write it as 1 by n, so that will become V by capital N, and so that's the volume per electron, and I can define this volume per electron in terms of a sphere of some radius Rs. Of course, that's a completely imaginary construction. It's some sphere of some radius Rs, and I can find out this Rs if I know what n is. So if you look at this expression for n, everything is known. The atomic mass is known, the metallic densities are typically known. The only information we need to put in is the number of valence electrons, the number of conduction electrons per atom. That is something that it is unknown, but for the moment. But these are the typical numbers that you get for the standard metals. These tables are all from Ashcroft. The pictures are all from Ashcroft, so you can follow the full table. It's only a partial table. There's a bigger table in Ashcroft. Please refer to that. Now, if you look at this, the electronic densities, that is the number per unit volume, those are extraordinarily high. Those are like a few times into 10 power 22, right? And those are very high densities, and that's 1,000 times or even more dense. 1,000 times or more than that, more than 1,000 times denser than a standard gas at STP, normal temperature and pressure. So, are you justified in using a simple kinetic theory of gases model for such a very dense solid? Is a question that you should ask right at the beginning, and the answer is, quite amusingly, it is not justified, but this simple mathematics that comes from the kinetic theory of gases works for a lot of applications, a lot of situations, but it also fails in many situations. It fails very big. So we should understand why it works in some places and why it does not work in some places, because we are not going to use any quantum theory here. So that's n. Then you also have that radius that associated with that volume, per electron. That radius is in angstroms is given, and the radius divided by the Bohr radius, 0.53 angstroms, is also given there, Rs by A naught. So you can see that comparatively 3 or 4 times more there is more space is available for the conduction electron in a solid compared to the electron in the hydrogen atom, roughly, approximately. Of course, these are all classical ideas, but still you should understand that 3 to 5 times more space is available for the conduction electron in a solid, in a metal. So now we'll go on to the assumptions of the Drude model. Electron ion interactions. Ion means the nucleus and plus the core electrons. That's called the ion. So the electron ion interactions are neglected. This is called the free electron approximation. Kindly remember this. I will be using these words, free electron approximation, several times in the course. Free electron means the electron does not interact with the ion. Then there is something called the independent electron approximation. This means that one electron does not interact with another electron. Whether it is conduction electron or valence electron, one electron does not interact with other electron. That's called the independent electron approximation. What this means is that I can simply study one electron, one conduction electron in a solid, in a metal, and assume that the whole metal will behave like that. I can just multiply everything by n, by the total number of conduction electrons. I will get the property of the solid. Of course, a very simplistic approximation. It's not correct in all times, in all situations, but we must understand what our understanding in this course should be. When does the free electron approximation fail? When does the independent electron approximation fail, and how we will fix it? So in the first condensed matter course, we will be dealing with free electron approximation and independent electron approximation, and we will also be dealing with many situations where the free electron approximation fails and how we fix it. In the second part of this course, which is an elective, the condensed matter 2 course, we will deal with the failure of the independent electron approximation in detail in the second course, which is a elective. Then in the Drude model, the electrons are assumed to move in a straight line between collisions. They are assumed to be governed by Newton's laws. They are classical objects. There is no quantum mechanics. Those are simple assumptions that are similar to the kinetic theory of gases. Those are the assumptions made. We assume that resistance, that V equal to IR, that R in Ohm's law, that resistance occurs. It's an assumption that occurs because of electron-ion collisions. That's an assumption. We assume that electron scattering is not important. This is an assumption, and amusingly, even if you use quantum mechanics, it remains true. And why it remains true is a very interesting explanation. We will come to that later. So these amusingly simplistic assumptions works many times. In many situations, accidentally it works. There is that's the way to use that correct word to use. Accident. It's a simple accident that the effects of quantum mechanics gets cancelled out, and you can use the simple classical idea. But in certain situations, if it fails big. There's no half measures here. If it works well. If it fails, it fails miserably. So we will now define a mean free path. That's the typical distance between collisions, L, and a relaxation time. That's the average distance between collisions. And just like in kinetic theory of gases, we will assume that this L and tau don't depend on the position of the electron and the velocity. Regardless of all that, it's the same. We will also assume that thermal equilibrium is achieved by collisions alone, because there is no other interaction, so it has to be from collisions with the electron-ion collisions alone. Then we will also assume that in a hotter part of the metal, the speed of the electrons that emerge from a collision will be large. That is, if the speed of the electrons are high in a region, that means that region has got higher temperature. If the speed is lower, that means it's got a relatively lower temperature, because that's the only way you can exchange heat with the surroundings. Finally, we will also assume that all the collisions are typically random. There is no directionality in the velocity. You can't in the absence of external influence. That is, if you heat a solid in one end and so on, there will be directionality in the collisions, in the directionality in the velocity. But in the absence of external influence, all the collisions are truly random. There's no way you can tell because we will assume that there will be thermal equilibrium can be quickly achieved by collisions, and there is no directionality. So these are the basic assumptions, and these are very brave assumptions in the sense that many people will laugh at it today. Today, with all the developments in our ideas of understanding of solid, many people, if you tell them this is how I am going to start modeling a solid, many people will laugh. But these brave assumptions actually work. And for those of you who are interested in pursuing theoretical physics as a career, this is a very important lesson for you, that when you need to make assumptions before you model something. And you have to make very brave assumptions. You can assume anything. You can assume that you can take a feather and use it as a hammer and drive a nail into a table using a feather. You can make any assumptions you want, but if those assumptions work, then nature behaves like that to a certain extent in certain circumstances. So this is a very nice example of how simple assumptions actually work. We will see how they work and where they don't work in later classes.